For a brief window in the radio spectrum, something appeared where 3i Atlas should be. Not a roar. Not a blast. A faint structured feature, just coherent enough to trigger alerts, just persistent enough to demand follow-up, and just strange enough to resist simple dismissal. Then, without ceremony or explanation, the universe stopped cooperating. Deeper observations, longer integrations, more sensitive receivers, all returned nothing. The mismatch between detected and now quiet became the central mystery. And in radio astronomy, silence is not the absence of a story. It is the beginning of one. The object itself is unremarkable by the standards of interstellar travelers. Catalogued as 3i Atlas, it carries no dramatic coma, no visible jets, no chaotic brightness curves. It drifts through the inner solar system with the steady indifference of debris, ancient, inert, and cold. But for a handful of hours, something in the radio band suggested otherwise. The signal was not broadband noise. It had shape. It had timing. And compared to the statistical texture of background fluctuations, it looked organized. Not artificial. Not intelligent. But organized in a way that demanded explanation. Radio telescopes do not see the sky the way optical instruments do. They listen to a restless electromagnetic ocean, where every frequency carries interference. Every band hums with planetary radio storms, satellite transmissions, ground-based radar, and the faint whisper of cosmic background radiation. To claim a detection is to claim that something rose above that noise, not just in amplitude, but in character. The feature associated with 3i Atlas did exactly that. It appeared in a narrow frequency window, persisted across integration periods, long enough to rule out a single sample fluke, and showed structure in time-frequency space that resisted immediate classification as terrestrial interference. Cross-checks were performed. Different antennas. Different processing pipelines. The signal remained plausible enough to justify follow-up. Then the follow-up began, and the signal did not return. This is where the story becomes uncomfortable. Science is built on reproducibility. A phenomenon that appears once and never again exists in a purgatory between data and artifact, between discovery and doubt. The teams returned to the same coordinates, the same frequencies, the same observing modes. Nothing. They expanded the bandwidth, adjusted the integration times, waited for different orbital geometries. Still nothing. They reprocessed the original data with updated calibration, searched for periodicities, tested for Doppler drift consistent with relative motion. The feature remained in the archive, but the sky refused to echo it. What does it mean when absence becomes the dominant dataset? In radio astronomy, non-detection is not merely failure to observe, it is a measurement. Every quiet observation places a constraint on brightness, on repetition rate, on duty cycle. If the signal was real and continuous, these follow-ups tell us it cannot be brighter than a certain threshold. If it was periodic, the upper limits on repetition constrain the timescale to hours, days, or longer. If it was transient, the observing windows cover enough phase space to suggest it was either extraordinarily brief or extraordinarily rare. The silence begins to acquire texture. It is not empty. It is a boundary around something we do not yet know how to describe. But before we can measure what is missing, we must reconstruct what was seen. The original detection was not a vague smear or a statistical whisper buried in post-processing. It had attributes. Timestamps locked to ATC, observing mode documented, bandwidth recorded, integration time known. The signal appeared in a specific frequency range, likely within the L-band or lower S-band, regions where interplanetary space is relatively transparent, but still vulnerable to ionospheric distortion and solar wind scattering. It was not a broadband flare. It was narrowband, or at least narrow enough to stand apart from wideband RFA. And it showed behavior in time. Either a slow drift, consistent with Doppler shift from relative velocity, or a structured pattern that repeated across adjacent time bins. Each of these attributes is a clue with two lives. A Doppler-like drift supports a celestial origin, something moving, something real, something beyond the terrestrial noise floor. But it can also be mimicked by instrumental effects, by satellite downlink sweeps, by ground radar modulated in frequency. A narrow feature suggests coherence, perhaps a natural maser-like emission or plasma instability. But it also resembles the signature of unshielded electronics, of switching power supplies, of communication protocols operating just outside allocated spectrum. Polarization, if measured, could hint at magnetic environments, at scattering through plasma, at orientation-dependent emission. But polarization can also be introduced by antenna side lobes, by reflections off nearby structures, by multipath propagation through Earth's atmosphere. The forensic challenge is not to explain the signal in isolation. It is to explain why the signal appeared when it did, behaved as it did, and then vanished. If we trust the detection, we must also trust the silence that followed. And if the silence is real, then the question transforms. We are not chasing a signal. We are chasing a condition, a moment in space, time, and geometry, when something briefly became visible. This is where perspective betrays us. Astronomy operates under a dangerous assumption, that the universe we observe is the universe as it is. But what we receive at Earth is not the source. It is the source filtered, scattered, delayed, and distorted by everything between us and it. The same object, emitting steadily, can appear loud or silent, depending on the path the signal travels. And in the case of 3A Atlas, that path was not constant. During the detection window, Earth, the object, and the Sun occupied a specific geometric configuration. Solar elongation, the angular separation between the object and the Sun as seen from Earth, determines how much solar wind turbulence the line of sight passes through. Phase angle, the angle between incident sunlight and the observer's line of sight, can alter how surface-reflected or forward-scattered radiation reaches us. Observing elevation affects how much of Earth's ionosphere the signal must penetrate, and at what angle. Each of these parameters changes daily. None of them were the same during the follow-up observations. If the detection was real, and the silence is real, then the source may not have changed at all. The geometry did. And if the geometry changed, then the propagation environment changed with it. Density, turbulence, scattering cross-section, multipath delay. What we call detected, then quiet, may simply be briefly aligned, then misaligned. The mystery advances by reframing. Perhaps nothing turned off. Perhaps the universe stopped lensing the signal toward us. Space is not empty. It is a medium, a dynamic, inhomogeneous, electrically charged plasma ocean. Radio waves do not travel through it unchanged. They scatter off density fluctuations. They refract through gradients in electron density. They are delayed, smeared, and modulated by turbulence in the solar wind. This is not exotic physics. It is interplanetary scintillation, observed routinely in pulsar timing, deep space communications, and heliospheric radio science. When a radio wave passes through a turbulent plasma, the wavefront becomes distorted. Small-scale irregularities act like moving lenses, briefly focusing or defocusing the signal. The result is scintillation, rapid fluctuations in received intensity, even if the source itself is constant. For a faint emitter near the detection threshold, scintillation can make it flicker into visibility and then fade below the noise floor. The effect is frequency-dependent, stronger at lower frequencies, weaker at higher. It is time-dependent, correlated with solar wind conditions, with heliospheric current sheet crossings, with the object's distance from the Sun. And it is directional. Different lines of sight through the same turbulent region will see different scintillation patterns. If the 3A Atlas signal was real, and the source was faint, then interplanetary scintillation could explain both the detection and the silence. The original observation may have coincided with a favorable scintillation peak, a moment when turbulence briefly amplified the signal above threshold. The follow-ups, observing through a different plasma state, would see the source as it truly is. Too faint to detect without assistance. This is not speculation. This is testable. If scintillation was responsible, then other background sources in the same patch of sky should have shown correlated intensity variations during the same window. Radio catalogs exist. Comparison data can be extracted. The hypothesis can be constrained. But there is another actor in this region of space, one that cannot be ignored. Jupiter. Not as a sensational trigger, but as a complicating factor. Jupiter is the loudest radio planet in the solar system. Its magnetosphere generates intense decametric bursts, driven by interactions between its magnetic field and its moon, Io. These emissions are not constant. They are modulated by Jovian rotation, by plasma torus dynamics, by solar wind pressure variations. And they occupy frequency bands that overlap with typical radio search campaigns. If 3I Atlas's sky position during the detection window was angularly close to Jupiter, or if the observing frequency coincided with the Jovian storm band, then contamination becomes a realistic concern. The signal might not have originated from the object at all. It might have been a Jovian emission, misattributed in position due to side-lobe response, calibration error, or spatial aliasing in the beam pattern. Follow-up observations, conducted when Jupiter had rotated to a quieter emission phase or when the angular separation had changed, would naturally return nothing. But the hypothesis cuts both ways. Jupiter's magnetosphere extends far beyond its visible disk. It distorts the local plasma environment, creates pressure waves in the solar wind, and can alter radio propagation conditions along sightlines that pass near it, even if Jupiter itself is not in the field of view. If the line of sight to 3A Atlas grazed the edge of Jupiter's magnetospheric influence, then the detection could reflect a genuine signal from the object, briefly enhanced or made detectable by propagation effects near the giant planet. The follow-ups, observing through a cleaner path, would see only the unenhanced emission, too faint to register. Discriminating between these scenarios requires precision. What were the exact frequencies? What was Jupiter's ecliptic longitude at the time? Was the object within the expected angular extent of Jovian radio emission? Did the feature show polarization structure consistent with magnetospheric origin? Or was it unpolarized like most interplanetary phenomena? These are not rhetorical questions. They are the investigative checklist that determines whether Jupiter is an explanation or a distraction. And then there is the domain we cannot ignore. The one that asks not what the universe did, but what we did. Radio astronomy at sensitivity limits is a discipline of subtraction. Raw data is never clean. It is contaminated by satellites, aircraft, ground transmitters, radar systems, power lines, switching electronics, and even the instruments themselves. Detecting a faint signal means removing all of this correctly without removing the signal. That process is automated, algorithmic, and imperfect. Candidate detection pipelines operate on thresholds. They flag features that exceed noise by some statistical margin. But thresholds are not truth, they are choices. Set them too high, and real signals vanish into the noise. Set them too low, and the pipeline floods with false positives. The 3I Atlas feature exceeded a threshold. It passed initial RFI rejection. It survived cross-checks. But that does not mean it survived all possible checks. There are known failure modes: unshielded electronics on board the telescope platform, unrecognized satellite downlink signatures, multipath reflections from nearby structures, atmospheric radio bursts mistimed in the calibration pipeline. Modern radio searches combat this with redundancy, multiple antennas, multiple observing epochs, comparison with archival data from the same sky region before the object arrived. If the team performed these steps, then the signal's credibility increases. But if any step was skipped, or if the observing mode during the detection differed from the follow-ups, then ambiguity remains. The signal might be a fragile glimpse of a real phenomenon, or it might be a mirror held up by our own tools. This is not dismissal. It is rigor. Every detection near the noise floor lives in this uncomfortable space until it either repeats or is explained. The scientific response is not to declare victory or defeat, but to map the space of possibilities with honesty. False positives are not failures. They are part of the process. They teach us where our instruments deceive us, where our assumptions break down, where the noise floor hides structure we mistake for signal. The mystery advances not by choosing an answer, but by refining the question. So we return to the silence. Weeks of observation. Different telescopes, different frequencies, different weather, different geometry. Nothing. The upper limits are now stringent enough to constrain a wide range of source models. If the emission was continuous and isotropic, it must be fainter than the thresholds reached during follow-up, perhaps orders of magnitude fainter than the original feature suggested. If it was periodic, the period must be longer than the cumulative observing time, or the duty cycle must be so low that the signal occupies less than a fraction of a percent of each cycle. If it was a one-time transient, then the detection captured a singular event, a flare, an impact, a plasma instability that has not recurred. Each of these interpretations is plausible. None can be excluded with the data at hand. And that is the weight of the silence. It does not eliminate possibilities. It narrows them, constrains them, forces them into uncomfortable corners of parameter space. But it does not resolve them. What remains is not a conclusion, but a constellation of constraints. A brief detection, suggestive, but not definitive. A long silence, profound, but not absolute. And multiple grounded pathways that could connect them. Source intermittency, propagation effects, planetary radio environments, human-made contamination. None of these explanations is allowed to win without evidence. The absence of repetition is treated as real scientific weight, not narrative inconvenience. This is where the story must rest, not in certainty, but in honesty. The point is not to claim what the signal was. The point is to understand what the episode reveals about how hard it is to listen through a living solar system. Radio astronomy is not passive observation. It is an active interpretation, of filtering, of reconstructing invisible events from distorted echoes. And sometimes, the universe answers in partial sentences. If future observations were to detect the signal again, same frequency, same structure, same timing, the case would strengthen dramatically. If statistical analysis of archival data revealed similar transients near other faint-moving objects, the phenomenon might generalize. If plasma modeling predicted scintillation peaks during specific geometric windows, the hypothesis could be tested prospectively. But until then, the data permits only this: something was seen, something stopped. And the silence that followed is as much a part of the mystery as the detection itself. We do not end with answers. We end with the humility that comes from confronting a cosmos that does not owe us clarity. 3 Atlas drifts onward, indifferent to our instruments, unaware of the brief electromagnetic whisper we thought we heard. Whether that whisper was real, whether it will return, whether it was ever meant for us, these are questions the universe holds close. And in the quiet that follows, we listen. We wait. And we remember that some of the deepest mysteries are the ones that leave us not with proof, but with doubt refined into rigor, and wonder sharpened into science.